We've learned about several different types of probability distributions. For example, we've talked about the Bernoulli distribution, the uniform distribution, the binomial distribution, and most recently, we've talked about the normal distribution. It turns out that the binomial distribution and the normal distribution are related under certain conditions. We will discuss these conditions, and we'll also see how we can use the normal distribution to estimate probabilities involving the binomial distribution. Let's start with a review. About 10% of the US population is left-handed. Suppose we sample 30 random US citizens. Let X represent the number of citizens in the sample who are left-handed. My first two questions are, the variable X has what type of distribution? And I would like you to find the expected value of X and explain its meaning. For the first problem, how I figure out the type of distribution is I start with the range. What is the range of X, which is all of the possible values? If X is counting the number of people in a sample that could be left-handed, it's going to range from 0, 1, 2, 3, 4, all the way to 30, because that's the number of people who can be left-handed in the sample. None of them could be left-handed, exactly one of them, exactly two of them, all the way to all 30 of them would be left-handed. The next thing I ask myself is, if I was to find something like the probability X is equal to 5, what does that mean? That's the number of people who are left-handed. What's the probability 5 are left-handed in the group? So you have a success, which is being left-handed, and a failure, which is not being left-handed. This is all a binomial distribution. Okay, so that is the type of distribution. It is binomial. You have success, failure. Let's find the expected value of X. Remember that for a binomial distribution, it's always n times p, where n is the size of the sample and p is the success probability. So n times p, 0.1 times 30 is 3. Expected value means we expect 3 out of the 30 citizens to be left-handed. Doesn't mean we're going to get 3 out of the 30 being left-handed, but that's like a baseline, what we expect to happen. Another way to think about that is if we repeated this over and over again, let's say we sampled 30 people 20 times. So we have 20 different samples of 30 people. In one sample, we may have one person who's left-handed, and another sample, we may have 4 people who are left-handed. But if we count them all and average them, then about 3 out of 30 will be left-handed. That would be the average. Let's find two probabilities. The probability X is 6, and the probability X is less than or equal to 6. Probability X is 6 means exactly 6 out of 30 people are left-handed. What is the chance of that happening? For the binomial distribution, we have a very specific formula. Whenever it says equals, we have to do 30 choose 6, multiply that by, well, we want 6 people to be left-handed, so it's the success probability raised to the 6. There's 30 people, 24 of them would have to be not left-handed, and that chance is 0.9. So 0.9 to the 24, if we multiply all this up, we'll get about 0.05. So there's about a 5% chance that exactly 6 out of 30 sampled citizens are left-handed. The probability X is less than or equal to 6. The probability 6 or less people in the sample are left-handed. Now, whenever we have less than or equals, that means none of them are left-handed, or 1 is left-handed, or 2 is left-handed, or 3 are left-handed. That's addition, right? So we'd have to add 7 different binomial formulas, because we'd have the probability X is 0, plus the probability X is 1, and so on. So we could do that by hand, or we could use something like Microsoft Excel or Google Sheets. We've talked about this in a previous video. We said that we just type equals binom.dist 6, 30, the success probability, true, and that will give us the probability X is less than or equal to 6. If you put that into Google Sheets, you'll get about 0.97. Please verify that you get that value. So there's about a 97% chance that 6 or less of the 30 sample citizens are left-handed. Now, look at the change between this slide and the last one. In the under review, that first sentence, it says we're going to sample N random citizens. So if I go back to the last slide, I had 30 exactly. Now I'm going to change it. I'm going to let N vary. What I want to do is look at visually what the probability distribution will look like for small values of N versus large values of N. Let's start with 3. Suppose we sample 3 random US citizens. Remember that a probability distribution can be a table where we write X and is probability. So X is 0, X is 1, X is 2, X is 3. Or we could see it as a bar chart like I have right here. Here I have 3 citizens. The options are X is 0, 1, 2, or 3, and the probabilities for each one. So there's a very likely chance that if we have 3 people, none of them would be left-handed. And then the probability one of them would be left-handed is close to about 0.3. And then you can see to have 2 people out of 3 being left-handed is smaller, is close to 0. And having all 3 people is very unlikely, is very close to 0. What can we say about this bar chart? It looks like the data is kind of right skewed because it has a right tail. Nothing remarkable about this graph. It's just we can see that the bars decline as we move to the right. But let's make that sample a little bit larger and see what the probability distribution will look like. Now, for a sample of 10 citizens, notice that the expected value, if we have 10 citizens, 10 times 10% is 1. And so that tallest bar is at the expected value of 1. And it looks like the bars do decline, just like on the left bar chart, but that first bar is a little bit shorter. If we make our sample even larger, 25 citizens, now we see something that almost looks symmetric. It's taking a more rounded appearance. And if I have a sample of 100 citizens, we will get something that looks like the normal distribution. So the binomial distribution, when N is large, starts to take the shape of the normal distribution. It turns out that whatever the success probability is, this will always happen. I'll give you another example. About 60% of the world's population resides in Asia. Suppose we sample a different amounts of random people. We're going to start with 3. Suppose we sample 3 random people from the world, and we just ask them, where do you live? And we count how many say Asia. That's what X is going to represent. So if 60% instead of 10%, 60% resides in Asia, the probability distribution for a sample of 3 citizens, this, with the small sample, this looks left skewed. When we have a small chance, like that 10% being left-handed, we'd have a right skewed graph. The larger this value is, the more left skewed it'll look for a small sample. But then for a sample of 10 citizens, if we go and calculate all the different probabilities, like the probability that 3 reside in Asia, 4 reside in Asia, 5 reside in Asia, and put it on a graph, we will get this nice rounded appearance. 25 citizens, 100 citizens. Turns out that it doesn't matter. Here I did 60%. In the last example, I did 10%. Choose whatever percentage you want. You will always get, for a large sample, a nice normal distribution. But it has to be large N. So a good question is, what is large? Right? Let's say you want to use the normal distribution to help you calculate probabilities. And, well, a large sample, if you were to go out and make a large sample, that requires time and money. You've got to pick these people out. It's very costly to get a bunch of different people and survey them. So is there a threshold? What does large mean? Is there a minimum value for which the binomial distribution looks like the normal distribution? Is there just like one number that works for all binomial distributions? For example, in this, when I had 60%, you can see with 100 citizens, it definitely looks like a normal distribution. For 25, it looks pretty good. Maybe it's not perfectly normal. Maybe somewhere between 25 and 100. But maybe it's closer to 10, because even at 10, it was starting to look like a normal distribution. So maybe it's something between 10 and 25. But with the example with the left-handed people, look at 25. 25 wasn't a perfect normal distribution. It looks like part of the left side is cut off. So definitely somewhere between 25 and 100 for that small percentage, that 10% probability. And then when we had the sample of 10 citizens, it definitely didn't look like a normal distribution. But when we had the 60% residing in Asia, you see, that looks more like a normal distribution. So maybe it has something to do with the percentage as well, and it does. So when our sample size is large, the binomial distribution resembles the normal distribution. What is large? If you have a success probability and you take whatever your sample size is and multiply by that success probability, if you get a number greater than or equal to 10, and the failure probability times the sample size is also greater than or equal to 10, then we consider this a large sample size, and that the binomial distribution will resemble the normal distribution. So when our sample size is large, we can use the normal distribution to approximate binomial probabilities. How do we use the normal distribution to approximate the binomial distribution? Well, remember, there are two things we need for a normal distribution. We need a mean and we need standard deviation. So we need some formulas involving the mean and standard deviation. So if I want to say binomial is equal to normal, I need to figure out a formula for the mean and the standard deviation, and also z-scores. So how we can approximate the binomial distribution is we can let the mean be the expected value of the binomial distribution, and the standard deviation is the square root of the success probability times the failure probability times the sample size. So for the next part of this video, we're going to do some examples where we use the normal distribution to approximate the binomial distribution. So let's go back to that example of 10% of the US population being left-handed. Suppose we sample 30 random US citizens, and X represents the number of citizens in the sample who are left-handed. My first question is, can I use the normal distribution to approximate the probability X is less than or equal to 6? I believe this was what we calculated earlier. And we were able to calculate this using the binomial distribution, right? I think we got about 97%. Can we use the normal distribution in this situation? Is 30 a large enough sample? Well, if I take 30 and multiply by 10%, the expected value is 3. And if I take 30 and multiply by the failure probability, I get 27. And those two numbers are not both greater than or equal to 10. So no, this particular scenario, this particular sample is not large enough. And if we were to look at the probability distribution, it wouldn't resemble the normal distribution enough in order to use the normal distribution to help us calculate this probability. So the answer is no. Both of these numbers need to be greater than or equal to 10. Here I have the same problem, but look at what I did. I changed the sample from 30 to 400. Is 400 large enough? And can I use the normal distribution to approximate the probability X is less than or equal to 52? It doesn't matter what probability I want to find. Let's just see if the sample, start off by saying, let's see if the sample is large enough. So I'm going to take 400 and multiply by 10%, and I'll get 40, right? That's 40 people are expected to be left-handed. If 40 people are expected to be left-handed, 360 would be expected to be right-handed. Both of those numbers are greater than or equal to 10. So since both of those numbers are greater than or equal to 10, we can use the normal distribution to approximate this probability. How do we do it? Well, for a normal distribution, we need a mean and we need a standard deviation. So the next thing we're going to do is we're going to find the mean, which is just the expected value, which is 40. And the standard deviation is a new formula. We're going to take n, which is 400. We're going to multiply by the success probability and then by the failure probability, and then find the square root of that. So n times p is 40. That's the mean. And then look at the standard deviation formula. It says n times p. I've got 40 times the failure probability, which is 0.9. If you multiply those two numbers together, the 40 and the 0.9, you get 36. The square root of that is 6. So now we have a mean and we have a standard deviation. Remember that z-scores, how we can find a z-score is we take our x value, subtract the mean, and divide by the standard deviation. Let's find the z-score for the probability x is less than or equal to 52. If I put 52 into the z-score formula, I subtract 40 and divide by the standard deviation, I get 2. The number 52 is 2 standard deviations above the mean. So what I'm going to do is I'm going to find the probability z is less than or equal to 2. You can pull up your z table, or you can plug this into Microsoft Excel. Either one will give you the answer. You need to be really familiar with how to find probabilities involving the normal distribution to get this right. So let's go over it one more time with Microsoft Excel. Okay, so I have Microsoft Excel pulled up. Remember, in order to use the normal distribution, we're going to type equals norm.dist. We put our z-score, which we said was 2, comma, the mean of the standard normal table is 0, the standard deviation is 1, and we're going to put true because we want the probability z is less than or equal to 2, and we get about 0.9773. So I have the probability z less than or equal to 2 is 0.9773. So there's about a 98% chance that our sample will have 52 or less left-handed people. So out of 400, if we have a sample of 400, there's about a 98% chance that 52 or less will be left-handed. Now, this is an estimate. This is an estimate of the binomial distribution. We can actually check to see if this value is close to the true percentage for the binomial distribution, right? How can we check? So the probability x is less than or equal to 52. We would type equals binom.dist. We want 52 successes out of 400 with a 0.1 probability of success, and we would put the word true, okay? If you put that into Microsoft Excel, you'll get about 0.9783. And with the normal distribution, we got 0.9773. So notice that we're really close. It's a little off, and that's why this is called an approximation. This is the normal approximation. Approximation means estimate. So we can get the same answer or something very close to it. We can use the binomial distribution like we've been using, or we could use the normal distribution, and they give us about the same thing. Let's see if we can fill in the blank here. The probability x is less than or equal to 52 is the same as the probability that what percent of the sample will be left-handed? So 52 out of 400, if you take 52 and divide by 400, you'll get 0.13. So if I asked you, what's the probability that 52 people or less are left-handed? I could ask that same question, just phrase it a little differently by saying, what's the probability that 13% or less of the sample? So 13% of the sample is 52. So whether I say, what's the probability that 13% or less of the sample is left-handed, or what's the probability 52 out of 400 are left-handed, 52 or less out of 400 are left-handed, you would still get 97.7% if you use the normal distribution. Let's try another example. We saw this example earlier. About 60% of the world's population resides in Asia. Let's sample this time 500 random people. So this is a pretty large sample, right? Let X represent the number of people in the sample who reside in Asia. Let's start by expressing X greater than or equal to 318 in words. So this is the probability that 318 or more people out of the 500 sampled reside in Asia. Now we can find this probability using the binomial distribution. But because the binomial distribution and the normal distribution are related, we could also use the normal distribution as long as the sample is large enough. So is the sample large enough? If we take 500 and multiply by 0.6, we'll get 300. And if we take 500 and multiply by the failure probability, which is 0.4, we'll get 200. So 300 and 200 are both numbers that are greater than or equal to 10. So the sample is large enough. Now let's approximate this probability using the normal distribution, and then later check your answer against the binomial distribution. Let's see if we get something close using the normal distribution. What do we need for the normal distribution? We need a mean, which we said is the expected value, is just n times p, and we need a standard deviation, which is the square root of the sample size times the probability of success times the probability of failure. So 300, remember that's n times p. You can double check that. 60% of 500 is 300. And then n times p times the failure. You find the square root of that, that's about 11. So the next thing we do is we find our z-score, 318. If I plug that into z, for the x value, subtract the mean and divide by 11, I get 1.63. So 318 is about 1.63 standard deviations above the mean. Now what we're trying to find is the probability x is greater than or equal to 318. So we want z to be greater than or equal to 1.63. These are the same things. Now, remember that the Z table that I provided you with and Microsoft Excel or Google Sheets, they only find probabilities involving less than equals. So what we need to do is we need to find the complement of this probability. The complement of Z greater than or equal to 1.63 is 1 minus the probability Z is less than 1.63. So we can put into Microsoft Excel equals norm.dist. We put 1.63, comma 0, comma 1, comma true. And if you put that into your calculator or your Microsoft Excel, you should get 0.052, or pretty close to that. Now, what I want to do is I want to check if this actual answer is accurate. To do that, we're going to do 1 minus binom.dist. We're going to put 318, comma, 500, comma, the success probability, comma, true. Put that in, you get 0.045. These are not the same because the binomial and the normal distribution are not exactly the same, but they're pretty close. So it's a good estimate for the binomial distribution. Let's fill in the blanks. The probability x is greater than or equal to 318 is equal to 0.052 is the same as there's a 5.2% chance that what percentage or more of the sample will what? So maybe pause the video and think about what I'm asking here. What do you think the two blanks will be? So there's a 5.2% chance So there's a 5.2% chance that 63.6% or more of the sample will reside in Asia. How did I get that 63.6? I took 318 and divided by 500. So 318 divided by 500 is 0.636. So I'm looking X being greater than or equal to 318 is the same thing as the percentage of the sample being 63.6% or more. So there's a 5.2% chance that 63.6% or more of the sample will reside in Asia.